In this lecture, we're going to talk about some applications of Hill functions, and we're going to start by talking about enzyme-substrate reactions. So for a little bit of context, this is how they work. They go through a cycle of several steps. We're going to start off with an active site that is provided by an enzyme. A substrate is going to bind into the active site. The reaction is going to happen, and the substrate will be converted into products. So in this case, separated into two and released separately. Once another active site becomes available, another substrate binds to it, and so on and so forth. We will go through this cycle as many times as the reaction will take place. There are a couple of things to note right away. First of all, if there are many substrates available, so the concentration is very high, the reaction will of course be faster because they will be binding to available active sites as soon as one actually gets freed up. Available sites will not be sitting idle for long. That's on the one hand. On the other hand, though, if the concentration of the substrates is really high, then there are not going to be enough active sites available to continue speeding up the reaction. So with high concentration, the actual reaction time will decrease because the active sites will be constantly occupied and not be able to provide any more of an actual increase in speed. So this is essentially the two basic ideas behind the Michaelis-Menten kinetics that describe the speed of a chemical reaction as depending on the concentration of the substrate. When there's no substrate present at all, the speed, of course, is going to be zero because nothing will be able to bind to the active site. However, with the high concentration of the substrate, the speed of the reaction will reach some maximal level. It will be quite fast at first and then will plateau out for the high concentration of the substrate. This already describes what we have seen in terms of behavior of the Hill functions, where we have a plateau or a horizontal asymptote that it will approach. And in fact, this is exactly what is described by Michaelis-Menten kinetics. Here is the formula for it. So x is going to be the concentration of the substrate, and what we have here is a linear Hill function with the graph they're going to produce in a little while, but has the same behavior as the actual Hill functions that we have seen before. A couple of things to note here about the people behind this law. There are two that are named after Michaelis and Menten. Michaelis, Leonor Michaelis, is a German biophysicist, and Menten, or Maud Menten, is actually a Canadian physician. So not only is she Canadian, she has very specific links to British Columbia and actually Fraser Valley in particular. She was born in Ontario, but her family moved fairly quickly after her birth to Harrison Mills in BC, and this is where she actually started her education. She received several degrees from Canada. She actually went to University of Toronto when she was an adult and received a Bachelor of Arts degree and then a master's degree in physiology. But at the time, it was nearly impossible for a woman to receive any higher degrees than that in Canada, so Menten had to travel abroad. She went to US, she went to Germany to work with Michaelis, where they came up with this law, and she came back to US to actually receive her PhD in biochemistry. She has quite a career, and she was known to be quite a character. In particular, she was very fond of arts her entire life, and she was very interested in learning different languages. And in particular, because she went to school in a small town in BC, a lot of her classmates were indigenous to the land, and one of the languages that she spoke fluently was Halkamelem, the language of the Stolo people. I encourage you strongly to look up the biography of both Michaelis and Menten because the people behind these discoveries are truly interesting characters. Menten is also, another fun fact about her, actually inducted into the Canadian Hall of Fame for medicine. So let's take a look at this function that these two scientists actually studied. And let's see if we can sketch it a little bit more precisely than my very hand-wavy previous sketch. We will analyze it the exact same way as we have before using the power analysis. So what happens for small values of x and what happens for large values of x. So for small values of x, let's start off with our function and think about the power analysis. On top, as in the previous as in the previous slides, there is nothing to choose from, so we have to keep the term that is currently there. On the bottom, though, we have two terms, the constant and the linear term. So again, for the constant, you can think of this as b times x to power 0, because this is just 1, but it will at least introduce the power of x so we can compare it to. For small values of x, small powers of x dominate, which means that we will ignore the larger power of x and keep the smaller one, which is just b. And it makes a little bit more sense if we rewrite this as a over b times x, because then it's clear that this is simply a linear behavior where the slope is a over b. What happens for large values of x? So for large values of x, our power analysis indicates that we should be keeping the larger power of the x available. So again, on the top, there's nothing to pick from, so we're stuck with the term we have. And on the bottom, the larger power is going to be x. Here, x's will cancel, so we will end up with just a. And as we have seen before, this will produce the Hill function that has a behavior near the origin that corresponds to small powers of x, or a line with slope a over b. So something that looks like this. And we can even annotate it saying that this has slope a over b. And then it continues on until for the large values of x, it has to behave like just a horizontal line at a. So it's going to reach this asymptote and approach that. So this is, of course, in line with our observations that with no substrate present, the speed of the reaction is in fact 0. But with high, and first, when the concentration goes up, the reaction speed goes up fairly quickly, but at very high concentrations, this is no longer the case. And in particular, we can notice is, let's say I start with a small concentration and I double it, the speed of the reaction will grow quite a bit from this speed to this speed, quite a bit of an increase. But if I start with a high concentration and I double that, if I look at the corresponding speed of the reaction, so the y-coordinates of these 2 points, they're much closer together. The increase in speed here was essentially trivial, right? So for small concentrations, the difference in the reaction time is big. For large concentration, the difference in the actual concentration is fairly small. The general Hill functions are, of course, of different degrees. So we start off with the linear as the Michaelis-Menten kinetics, but we can also think about various chemical reactions taking place that will probably correspond to slightly different behaviors that are also described by Hill functions. So let's take a look at what would these look like if they are all sketched on the same graph. Now, of course, again, the analysis is going to be the same. We have to think about the small values of x, and we have to think about the large values of x. And so for each one of these functions, let's take a look at what the behavior is going to be. So I'm going to make this big table, and I'm essentially going to line it up to the functions that I have up top so that I can fit them in nicely and aligned. Okay, in fact, I actually encourage you to pause the video right here and fill this table out by yourself, because this is simply going to be, once again, using the power analysis that we have already seen before. Okay, so for small values of x, the small powers dominate, and the small powers on the bottom of all of these functions correspond to the actual constant. So for this function, for small values of x, we're going to have ax over b, ax squared over b, and ax cubed over b. Now, it might be easier if we rewrite these as a coefficient times the x. So instead of saying it's ax over b, it's probably more straightforward for graphing to say that I'm going to separate the coefficient and keep the power of x. Same thing here. It's going to be a over b times x squared. That way, it's a little bit more clear what the actual graph will look like. And so finally, for the last one, I'm going to have a over b times x cubed. Now I see that this is just a line with slope a over b. This is just a parabola that has been stretched or transformed with this factor. Now remember that a and b are both positive constants, so this is still a parabola looking up. And this is a cubic, snaky function that again has been stretched out as according to these constants, but them both being positive means that it's going to be our regular snaky shape. For large values of a, the large powers of all the denominators will once again dominate, and so we're going to end up with ax over x, ax squared over x squared, ax cubed over x cubed. And of course, notice that in each one of these cases, the x's will cancel themselves, leaving a as the AND behavior for all of these cases. Okay, so now let's put all of these three functions on the exact same graph. So once again, because of the actual applications that we're going to be working with in terms of Hill functions, I am only interested in sketching this graph for positive values of x. So I noticed that all of them are going to have a as their horizontal asymptote. So I'm going to have the a as the horizontal line going here. And now let me start drawing from the smallest power of the Hill function to the larger. So this first one, we have to have a near origin behavior as a line of slope a over b. So I'm going to start off with a straight line. And then, of course, I have to once again approach this asymptote. So as in the example before, I'm going to start with the linear function, and then I'm going to carry over in order to approach the asymptote. So this is my linear f of x. That's the name of this one. Now, next up, I have a quadratic. So that means that near the origin, this function has to look like a parabola. But then for large values of x, it has to approach a. So this is where the other part of the power analysis is important to remember. For large values of x, these both approach the same number. But for small values of x, they are linear versus quadratic, which means that in the beginning, the smaller power will dominate, so the linear function will be on top. But later on, the larger power has to switch over and start dominating. The quadratic function will eventually have to beat out the linear function in how fast it grows. So I'm going to have a switch over at some point there. I start off with a parabola, and then at some point I switch over to dominate the linear function. So this is going to be my quadratic Hill function, that's in this case called g of x. And then my last case here is the cubic. So near the origin, it's going to behave like a cubic function, and I have to decide where it fits, right? So once again, the power analysis says that near the origin, the smallest power will dominate, which will be linear, followed by the quadratic. And so the highest power will be the flattest near the origin, but at some point it will have to switch and start growing faster than any of the other two functions. So this is going to be the case with my cubic. I'm going to start at the bottom here, going to switch over, and eventually dominate both. So this pink one is going to be my cubic function that is called h of x here. Okay, this is really a great way to think about how the different Hill functions interact with each other. The near origin behavior is described by the smallest powers in the denominators actually dominating. The end behavior is always approaching a constant, so always this kind of saturation limit in terms of chemical reactions. And the switch point is governed by the same laws as any other switch point for the actual polynomial functions. The smallest power dominates near the origin, and then the largest power dominates for large values of x. Let's take a look at another example of the interactions between the two different Hill functions. So the switch point that we've been describing is, of course, in terms of, for example, chemical reactions, probably that concentration level where the reaction stops speeding up and starts plateauing. It's a rapid transition from one state, so speeding up of the reaction, to another, slowing down. Here we have two Hill functions, second degree and fifth degree Hill functions. We are wondering about a number of different things. Where do they intersect? What are the asymptotes? Where do they increase and decrease, and which of them increases the fastest? And which one has the sharpest switch point? So that point where the reaction described by the functions, for example, begins to slow down. Which one does it faster than the other? This example is really meant for your own work. So please pause the video, attempt it for yourself, and then come back for a quick overview of how to approach this. Okay, so first of all, let's actually sketch the two functions so we have some idea of what the visual representation of them is going to be. Of course, you can pull up Desmos and draw it on Desmos. I strongly encourage to do this by hand for first little while, just to really get a handle on how these functions behave. So for the square one, near the origin, we're going to choose the smaller power on the bottom to dominate. So near the origin, it's going to be x squared over 1, which means that near the origin, it's going to behave like a parabola. For large values of x, we're going to pick the larger power to dominate on the bottom. So x squared over x squared will result in 1 as the asymptote. So I'm going to start off with a parabola behavior and eventually approach the 1 as the end behavior. So this is my graph for y1. What about the graph for the fifth degree? Well, for small values of x, the smaller power on the bottom is going to dominate. So we have x to the fifth over 1. So my function looks like x to the fifth. Remember that odd powers all look like the sneaky functions. So it's going to look like that near the origin, right here. And then for large values of x, we're going to pick the larger power to dominate on the bottom. So we're going to end up with x to the fifth over x to the fifth, which of course is 1. So it approaches the exact same line of y equals 1. Now, once again, we have to decide x squared and x to the fifth near the origin. So near the origin, the smaller power will dominate, which means that x to the fifth has to lie below my parabola. And then at some point, it's going to switch and take over the actual domination, right? So it's going to be something that looks like this, y2. Excellent. What we're interested in here, of course, is somehow thinking about this particular switch point somewhere here. Okay, so this is my switch point. First part of the question asks precisely that. Where do these functions intersect? Again, they might actually intersect on the other side too. I'm much less interested in that. Here, though, it's also pretty clear that they won't if they continue behaving in the way that we've indicated near the origin. In order for us to find where they intersect, we have to set them to be equal to each other. So x squared over 1 plus x squared has to equal to x to the fifth over 1 plus x to the fifth. And this is the equation we now have to solve. What we can do here is we can cross multiply. And so what we're going to end up with, I'm going to combine two steps. I'm going to cross multiply and open the brackets in the cross multiplication right away. So x squared times 1 is x squared plus x squared times x to the fifth is x to the seventh. So x squared plus x to the seventh. And then the other cross multiplication will give me x to the fifth plus x to the seventh. Well, this is quite convenient because x to the sevenths can cancel each other out. If I move everything over to one side, I'm going to get x to the fifth minus x squared equals to 0. If I factor things out and do so properly, please do not divide, factor, I'm going to see that I have two roots, 0 and 1. And that is supported by my picture here. The functions intersect at 0, and the functions intersect at some other switch point. So according to my calculations, this particular switch point is actually 1. Okay, so my scale on the x and y axis here is not actually equal. That's totally fine, because again, these sketches are more qualitative than anything. What about part B of this question? What are the asymptotes of these functions? So we are only seeing one particular behavior for the functions, and that is the behavior near the infinity. And what we can see is that for large values, both y1 and y2 approach 1. So for large values of x, we see that y1 and y2 approach 1 as their sort of final value here. Okay, part C, what do we have? Which of these functions increases fastest near the origin? So we already had to think through this when we were drawing the graph, but let's think through this again. Fastest near the origin means what one is dominating. Near the origin, we care about small powers. Small powers will, of course, mean that it's the quadratic function that dominates near the origin. Okay, so I'm not going to write it down in the full sentence, but I'm just going to say that smaller power dominates near the origin, which means that the function that grows faster is going to be y1. And then finally, part D, which is the sharpest switch and why? So let's take a look at the switch here. So what that means is the sharpest, meaning at which, like if we look at how fast each of these increases, which one sort of increases the fastest at the switch point? Well, thinking about what switch point represents, it's where the larger power goes from being dominated to dominating. So it has to cross from being underneath to being on top. So it's by definition got to make that switch faster than the other function because it actually has to surpass it. It has to overtake it. And due to that, it's of course going to be the larger power that has the sharpest switch, right? So let's write half a sentence down here. Larger power dominates after the switch. So it has to go from being dominated to dominating after the switch. And in order for this function to jump and actually surpass the other one, it has to actually have the fastest increase here. So here, y2. Okay, again, just digging in a little bit deeper about what it means to have two different Hill functions and how they will interact with each other. Let's take a look at another example. This is actually from the final exam from a couple of years ago. So let's take a look at how we can work our way through it. A rate of enzyme catalyzed reaction follows Michaelis-Menten kinetics, as we've discussed. So we know already that it's going to be represented by a linear Hill function. That's Michaelis-Menten kinetics. And we have the following two properties. When the concentration of the substrate is low, the rate of the reaction is approximately 2x, where x is the actual concentration of the substrate. So here we have two pieces of information. When the concentration is low, the function looks like 2x. And the second bullet point says when the concentration of the substrate is very high, so on the opposite end, the rate of the reaction approaches 10. So for high values of the concentration, the rate approaches 10. Now remember that the Michaelis-Menten kinetics are described using the linear Hill function. So all we have to do now is match the low and 2x and high and 10 into what that means for the values of a and b, which is exactly what the question is asking to find. So first of all, thinking about my general function, what happens for small values of x? Small values of x, nothing out of the ordinary here, just the same power analysis. For small values of x, what we have is that my function, which is ax over b plus x, remember, small values of x, small powers dominate, which means that it's the constant on the bottom that will dominate, and I'm going to end up with ax over b. What the information is telling me is that for low concentration, so small values of x, my function has to be approximately 2x. So that means that ax over b has to be approximately equal to 2x. So I know that a over b is actually equal to 2x, right? I can get rid of the x's here. A over b is 2. Excellent. Let me move this a little bit over so it's less awkward. There we go. On the other hand, we know something about high concentration of the substrate. So we once again think about what that means for large values of x. And in terms of our function, we're going to have ax over b plus x. But now the bigger power dominates on the bottom. So this will leave us with the x. The x's will cancel, and that will give us an a. Perfect. So for large values of x, I have that my function behaves like a. And the information here says that when the concentration is high, the reaction rate approaches 10, which means immediately that A is equal to 10. Well, perfect. If A is equal to 10, I can plug it into here. And what is my B going to be equal? So I'm going to have 10 over B is equal to 2, which tells me, of course, that B is equal to 5. And that is my answer. The A value is 10 and the B value is 5. Okay? A straightforward application of the power analysis and the actual interpretation of the information given.